Okay guys, we're going to do introduction little video lecture for our acid-base unit today. That way we get a little jump start on the unit and you guys come in with a little bit of knowledge, so when we get to class tomorrow we can jump right into doing a demonstration and then doing some practice stuff. So Unit 13, we're dealing with acid-base chemistry, so we're going to be talking about acidic properties, basic properties, how they interact with each other, what makes them the same, what makes them different, deal with the pH scale. We'll do a lot of equilibrium stuff in here, and basically give you guys a pretty good introduction to how the world of acids and bases work. So we'll be in chapters 19 and 20 as we work here, so plan on 2 online quizzes and 2 book assignments for this unit. Also, we'll be running probably about 3 weeks for this unit, so it'll bring us up to the middle of May, with hopefully a full week of time before the finals to talk about nuclear chemistry. So that's our plan for the trimester. So here we go. First thing we want to talk about is the properties of acids and bases, and take a look at how are they the same and how are they different. One of the major misconceptions of acids and bases are that acids are bad for people and bases are good. That's a misconception. That is not true. If we take a look at our properties, acids, if you actually taste an acid, it would taste sour. If you taste a base, it would taste very bitter to you. So we know the rule is there's no eating in chemistry. In lab scenarios, there's no eating. But believe it or not, back in the 1800s, 1700s, that timeline, one of their tests for properties was to actually taste chemicals. That led to some interesting issues. Chemists had chemical burns in their mouths. They suffered from, different cancers, that kind of stuff, where their research actually kind of hurt them, or maybe even killed them in some cases in terms of that stuff. Madame Curie, for one person alone, did all her research on radiation, that kind of stuff, with no protective equipment. So in her world, she basically gave herself cancer by doing the research that she did in terms of the protons, neutrons, and how atoms all work. So we're a little safer these days, and now we know that you really have to protect yourself against chemicals. So we don't taste anything in lab. However, there's a lot of acidic foods out there, and the foods you eat that taste sour are usually acidic in nature, and those foods that you taste that are very bitter to you are going to be bases in nature in terms of the actual food chemistry there. So now, in terms of what they look like to you, they both look just like water. So it's really interesting when it comes to how they appear, because they're just a clear liquid when they're in solution. And it makes it kind of dangerous, because if they're very concentrated or not concentrated, in either case they look identical. So that's why we need to use things like pH paper and indicators and pH meters to figure out how acidic something is, to figure out how dangerous it is for us to work with. So one thing about bases that make them a little bit different is if you touch a base, it feels slippery. Acids, not so much, you wouldn't notice that, but for a base it actually would feel slippery to the touch. All of our soaps, detergents, a lot of our cleaners are bases. So any of those cleaners you use, those soaps you use that feel slippery to you, that is, you're using a base probably in your cleaning supplies. Next one down, corrosive to humans. Notice how they're both corrosive to humans. Make sure you jot a little side note here, something that acids are bad for you, bases are bad for you also. They're both, detrimental to you in terms of they come into contact with our skin, if we consume them, those kind of things at high concentration. They both will react with human or organic material and deteriorate or break down organic material. So it is not true that acids are bad for you but bases are good. Actually, some of the more serious chemical burns that I've witnessed and seen have been from people who've been exposed to bases, not so much acids, because bases we can deal with in a powder form, whereas acids we're always doing a liquid form. So in a powder form, people have a tendency to feel like they're safer, so they touch them, and then that base gets on their hands, and then it actually starts to react with your hands, and then actually cause a chemical burn. So I don't know if you guys have ever watched the movie Fight Club. I'm sure most of you have not, but if you happen to have seen that movie from I believe it was the early 2000s, there's a scene where Brad Pitt and I think it's Edward Norton in it, and he puts a base on his hand after he kisses his hand, and it gives him a massive chemical burn. Now it's obviously Hollywood, so in Hollywood they make it seem a lot worse than it actually is, and they make it look a lot worse than it actually is. But what they're doing there is they're basically showing the properties of a base, where you actually have sodium hydroxide, which is a very strong base. That's the powder they put on their hand. And if you remember in the video, the way they cleaned it was by putting vinegar on top of it, which is a very weak, dilute form of an acid. So they actually used an acid to help, stop the chemical process of the base. So, take-home message is not to watch Fight Club. That's up to you and your parents once you turn 18. I think it's a rated R movie. You could probably watch it. I don't know. But it is corrosive to humans. Both of them are. So we got to be careful with those when we work with them in lab. Both of them have the ability to react with metals. Acids will always react with metals. Okay? When they react with metals, you identify that by the production of hydrogen gas. Okay? So acids, when they react with metals, it's a single displacement reaction where the hydrogen gets replaced by the metal goes into solution, and the hydrogen gas gets released. So one way to distinguish if you have an acid or a base is if you do put a metal with a solution and you get the production of hydrogen gas, you know that you had an acid that you were working with. Bases can react with metals. They may or may not react with metals. It really isn't one of their properties. It's more the issue if you happen to have a hydroxide ion, that negative hydroxide ion, with like an alkali metal, where the base just might happen to do a single displacement reaction because of the properties of the metals there. So it's possible that bases react with metals, but it's not because of being a base. It's because of the cation that the base is attached to in that scenario. So, and again, both of them are electrolytes. So both of them are going to, when they dissolve into water, they're going to split into their ions. And when they split into their ions, then they're going to be able to carry that conductive electronic charge. So both of them act as electrolytes. So as you kind of can see, there isn't a lot of differences in terms of your physical properties that you can see in there out in the open like that. So there's other things that we have to do to determine what distinguishes between an acid and a base. And what it really comes down to is how do they ionize in water. So what do they do to that water solution, and what type of equilibrium do they establish? So for bases, they establish a very different equilibrium than acids establish inside a water solution. And we can track that equilibrium by measuring pHs. So we'll get into pH, that kind of stuff also. So last piece on this slide, acid-base chemistry always done in solution. Okay, so we won't always write it in our equations, but we assume aqueous on everything for acid-base chemistry. So we're always going to be an aqueous solution. So water will always be around. It may or may not be written as part of the equation, depending on what we're talking about, but we're always done in solution there. All right. We do need to remember how to name these things. Now, we've gone over naming in our previous units, but I want to hit it real quick again for everybody to get a quick review, because I'm not going to cover this in class, and if you don't remember how to do the naming for acids and bases, then you need to either go back to our notes from previous units or kind of do some review here. So, first of all, we have two different types of acids that we'll be naming. We have monoatomic acids, or where their anion is a single, and you have polyatomic, where the anion is actually a polyatomic ion. So our example here is hydrochloric acid, where we have hydrogen, and our anion is chlorine. So we have that chloride ion. When we name a monoatomic anion acid, like HCl, we start with the prefix hydro, and then we use our normal root word, so here it would be chlor, and then we put ic on the ending for acid. So HCl is hydrochloric acid. If we had H2S, so a hydrogen with the sulfur, that would be hydrosulfuric acid. If we had H3P, that would be hydrophosphoric acid, and so forth. But the hydro in front tells us that our root word is a single anion, so this is just chlorine. Now, if you don't use the word hydro up front, then you get into polyatomic anion-based acids. If you recall, we have two different main ways to name polyatomic ions. We have an ate ending and an ite ending. When they end in ates, okay, all we do is put the root word with ic in the end. So if we have ClO3, that's chlorate. So chlorate would be turned into chloric acid. Notice how there's not hydro up front anymore. So this is just chloric acid. If you have the ite ending, we use us instead for the acid. So ClO2 is chlorite, so we call that chlorus acid. So it's not in the notes, but there are possibilities, especially with the chlorine, that we have a hypoite. So if you remember that, hypoite would be ClO, just ClO. So in that case, we actually keep the same naming system. We would just call it, if it was just ClO without the 2 here, that's called hypochlorite. So the acid would be hypochlorous acid. So we just use the same prefix hypo out front to indicate the hypoite polyatomic ion. Okay, that's real quick, guys, for the acid stuff. But we did this early in the year, so you have notes on it. We've practiced it in our worksheets. If you need additional practice, check the book. It'll have some for you. Come talk to me. I can give you some extra practice, so make sure you can get the naming stuff down. Now, bases. Bases don't have a special naming system. Bases are named just like any other ionic compound. So as long as you're able to name bases, you're fine. Typically, a lot of the bases we will be dealing with are hydroxides, so that OH with a 1- charge on them. So a lot of our bases are like sodium hydroxide, potassium hydroxide, magnesium hydroxide, those kind of things. Not all bases have hydroxide in them, but a lot of the a lot of the stronger ones do. So we'll be dealing with a lot of hydroxide word bases. So it won't be bad maybe to jot down bases, usually hydroxide. It doesn't have to be, but a lot of them will be that way in our unit. Okay.